going to talk a little bit today about the t distribution, or I should say the family of t distributions. There's one for every sample size n. And we use them to form confidence intervals and later to do hypothesis testing. But for now, to do confidence intervals for unknown population means mu, where we're in the more typical situation that we don't know sigma. We don't know the population standard deviation. And I think it makes sense that we, in general, would not know that if we don't know the population mean. So when we don't know sigma, we have to approximate it with information from our sample. So we use the sample standard deviation, that's called, or the notation is little s. And we substitute little s where we used to have a sigma in the confidence interval formula. So if you take a look, S is here, and here, and here. Those used to be sigmas. If we knew sigma, we would use it. And when we replace sigma with S, unfortunately, that means we can't use a normal distribution anymore because using S introduces more variability into our estimate. So instead, we have to use what are called t distributions. And I've made a sort of exaggerated picture here on the stack crunch video. It's a little bit more realistic, but the idea is just to show you that a t distribution looks very much like the standard normal distribution in that it's bell-shaped and symmetric and has mean 0. The difference is that a t distribution has fatter tails, right? So the more variability means we sometimes get more extreme values. Well, we get them more often. So for a standard normal, it might be really unusual to have an observation out to 3 standard deviations away from the mean. We would have more of those kinds of observations when we use t distributions. Right? So symmetric, bell-shaped, centered around 0, mean of 0, but fatter tails, more probability for extreme values. Now, none of this really changes a lot in the way we actually create a confidence interval because we need to use technology to figure out the confidence intervals just like before, except now when we go to find the critical value, we use a different distribution in StatCrunch. We use t distributions. So just as a reminder, the critical value is the one that captures the middle C% of the area under our distribution. The C is the confidence level, so if we want to capture, if we have a confidence level of 95%, we need to find the critical value that captures the middle 95% of the probability or area between that value and the negative of that value. When we have a standard normal distribution, we call that a z-score. Here, since we have a t distribution, we'll call it a t-star or t-score, sometimes t-value. But that's the value for the t distribution, and we have to be specific about the t distribution that we're using. It's the one with n minus 1 degrees of freedom. So that's the value that captures the middle C% under the t distribution. So if I pictured it, I would have a minus t star to t star, and in between, right, I would capture C% of the area under the particular t distribution that we're using. We have one extra bit of vocabulary that I think you'll need to add to the notes. Right, the margin of error is still the critical value times s over root n, which used to be sigma over root n. The fact that we're using s means that instead of sigma over root n, we have s over root n, and we give that its own name. That's called the standard error. Right, so that's new, or sometimes just SE. And so the margin of error is the standard of error times the critical value. All right, our first example, finding a t confidence interval, was trying to estimate the mean IQ of a population, now assuming that we don't know what the standard deviation sigma is. And so we'll just use the formula for the confidence interval, and we'll get x bar 98 plus or minus. Now I need the t-score for the middle 95% of the t distribution with 99 degrees of freedom. So I do that in the StatCrunch video. If you watch that one first, you already know the result. If not, you'll see where this comes from. But the t-score is 1.98 for the middle 95% of that t distribution, very close to a standard normal, which would be 1.96. And then I have to multiply by s over the square root of 100, which would just be 10. And then if I use my calculator, I can get the actual endpoints of the interval. So let's see, I'm going to have 1.98 plus 1.98 times 16.5 divided by 10 is 101.267. Use 3 for that. And 98 minus 1.98 times 16.5 divided by 10. So I get 94.7. Right, so this would tell us that we are 95% sure that the mean IQ of the population is between 94.7 and 101.3. And just like before, right, there are trade-offs. If we want to be more confident about our estimate, then the interval expands. Right? So we can be more confident, but we have a less useful interval because it has a wider range. If we want to shrink the interval and keep our level of confidence, the only way to do that is to take more in the sample. But taking a larger sample means more expensive and more time consuming. So there's always this trade-off in estimating between how accurate you want to be, how sure you want to be, and what you can afford to do with the time and money you have. Okay, example 2 continues the shelter dog example, only this time we want to find a confidence interval for the mean weight where we don't know the standard deviation of the weight. Right, so instead of sigma, we'll use the given sample standard deviation of 8.3. So our confidence interval would be 27, that's x bar, plus or minus the t star, which was 2.72 from StatCrunch. That was for the middle 99% of a t distribution with 35 degrees of freedom. Right, multiply by sample standard deviation, 8.3, with the square root of the sample size, which is 36. And let me just finish this up. 27 minus 2.72 times 8.3 divided by 6 gets me 23.24. And the right-hand endpoint is 30.76. So after creating that confidence interval, again, it's really important to understand what it means. We can be 99% sure that the true but unknown mean weight of all shelter dogs is between 23.25 pounds and 30.75 pounds. Okay. So it's a fairly wide range, right, from 23 to 30 pounds. But we're also really sure that the true mean is really in there. So if we wanted to tighten that range up and still be that sure, then we need more than 36 dogs in the sample. All right, so those are, I think, good examples to get you started for the worksheet, and then the Pearson assignment as well. If you have questions, then please let me know. See you in class.